Hello and welcome. My name is Noah Deere, and this is Lesson 18, Surface Area for Portland Community College's Math 254, Vector Calculus 1. To begin this lesson, we will do some introduction and formulation of how we even compute surface area. What we're going to see is that this is easiest to start with when we have a surface given in parametric form, and then we're going to go ahead and look at finding the parametric forms of different types of surfaces so that we can use those in order to find the surface area of those given regions. And then we'll go on to finding surface area for a function in two variables. That is, we will use the formula that we come up with for surface area of functions given in parametric form in order to find the formula for surface area of a function in two variables, and then we'll use that formula to find some surface areas for functions in two variables. All right, let's jump in here. Section 18.1, Introduction and Formulation. So given a surface, given in parametric form, so vector r of u comma v equals x of u comma v, y of u comma v, and z of u comma v, with the domain D equals A to B in the u direction and C to D in the v direction. Right, so let's keep in mind that this is our u interval, and this is our v interval. So it can be of interest to compute the surface area of the surface over some given domain. In order to compute this area, we will begin by cutting the domain into subrectangles r sub I comma j equals u sub I comma u sub I plus 1 crossed with v sub j to v sub j plus 1 in the v direction. So our area of these different subrectangles is delta A equals delta U times delta V. Let's keep in mind as we're doing this that this is not actually really seen on our surface. This is not x values or y values or z values. These are the u values and v values that are the inputs for the function r that give us the x, y, and z values. So our domain is in another space that we really don't exactly see as equally sized rectangles on the surface in question. So for example, we're going to look at this graph here in just a few moments. We can see that these rectangles that we have are not exactly rectangles. They are actually curved to some degree, and they are all of different sizes, but they are with equally spaced u values and v values. So I think the u values are going to the left here, and the v values are going kind of upwards in this direction. So we want to keep that in mind as we're thinking through all of this. So we cut the domain up into these little subrectangles, and when we do this, we simultaneously cut the surface into patches. So the patches are different than the subrectangles, right? The patches are what we actually see on the graph here. So here we see the patches given by the subrectangles that are in the domain that we don't exactly see. So the patches that we have are s sub I comma j equals the interval of r sub u sub I comma v sub j to r of u sub I plus 1 comma v sub j. So these are, we're just moving now in the u direction, and then crossed with r of u sub I comma v sub j to r of u sub I comma v sub j plus 1. So here we're moving just in the v direction. So we get these patches as we move our domain from u sub I to u sub I plus 1 and from v sub j to v sub j plus 1. That shows us these actual patches here. So if we fix v sub j, let's look at delta r as we move by delta u, right? So if we fix v sub j, and then we're just going to move by some amount in the u direction, delta u, then delta of r sub u equals r of u sub I comma v sub j minus r of u sub I plus delta u comma v sub j, right? We've just moved a little bit in the u direction, and that's it. Well, this is approximately, this is our partial derivative with respect to u. Sorry, I might be sniffling a little bit. I'm getting over a cold. And so this actual difference in our r value as we move by u a little bit is approximately r sub u, the partial derivative of r with respect to u, times delta u. This actually comes from the definition of this partial derivative. Remember that r sub u equals the limit as delta u goes to 0 of r of u sub I plus delta u, comma v sub j, minus r of u sub I v sub j. I think I'm squeezing that into the edge of the picture here, all over delta u. Okay, so since our partial derivative is equal to this, if we multiply by the delta u over and get rid of the limit, then we get an approximation here. So that's where this approximation is coming from. Similarly, if we fix u sub I and move by delta v, we'll get that delta r sub v is approximately the partial derivative of r with respect to v at that u sub I v sub j times delta v with a similar argument, right? So we don't need to go over that again, hopefully. Then the area of the patch can be approximated by the area of the parallelogram determined by delta u times r sub u of u sub I v sub j and delta v times r sub v of u sub I v sub j. So let me add kind of a little bit of a step in here. So we have a parallelogram. If we move by delta u just a little bit, then our actual surface is going to move by delta r sub u and delta r sub v, right? We're going to move a little bit in the u direction and a little bit in the v direction. We're actually going to be out here. I want to change colors. So this is delta r when we move by both u and v, is this the red line going out to the opposing corner of the parallelogram. But this parallelogram that we get by delta r sub u and delta r sub v, this is essentially the surface area that we obtain by moving by both delta u and delta v. This is an approximation to that surface area. So what we'll do is we'll let the limit as delta u and delta v goes to 0 to get instantaneous surface areas and then add all of those up, which is going to take an integral, right? So we just showed that delta r sub u is approximately r sub u times delta u, and that delta r sub v is approximately r sub v times delta v. So let's add those to this picture here. So this is approximately r sub u times delta u, and this is approximately r sub v times delta v. So if we can get the area of this parallelogram constructed by these two vectors, then we'll go ahead and be able to take a limit and work out the total surface area of the region in question. So that's what we're saying when I say that the area of S sub I comma j can be approximated by the area of the parallelogram determined by delta u times r sub u and delta v times r sub v. And since the parallelogram's area is equal to the magnitude of the cross product of the vectors which determine them, we get, right? So that's just to remind us that the area of a parallelogram equals the magnitude of the cross product of the vectors that determine that parallelogram, right? So this is just a review of how we get the area of a parallelogram. So since the vectors we're looking at are r sub u times delta u and r sub v times delta v, the area of one of these parallelograms is going to be approximately the magnitude of delta u times r sub u crossed with delta v times r sub v. Now delta u and delta v are constants, and properties of cross products allow us to factor these out of the cross product. So we're really looking at that this equals the magnitude of r sub u crossed with r sub v, all then times by delta u delta v, but delta u delta v is delta a, the change in our area. So we can write that this equals the magnitude of r sub u crossed with r sub v times delta capital A. Okay. So we're getting somewhere now. Summing the areas of all the patches and letting the delta U and delta V go to 0, we get the total area of the surface in question over some given domain to be A of S equals, the limit is m and n go to infinity of the sum from I equals 1 to n and j equals 1 to m of the magnitude of r sub u crossed with r sub v times delta A, which equals the double integral over our given domain of the cross product of r sub u crossed with r sub v d capital A. Right? So essentially we just go through all of this talk here in order to come up with this little formula, and now we're going to apply this formula in a few different scenarios. Let's actually go ahead and look at this GeoGebra graph real quick before we do jump into those examples. Oops. Here we go. So here's some u sub I, v sub j, and here are the vectors r sub u times delta v and r sub u times delta u, and then this is the parallelogram that we're talking about, and we would do this over and over again and add up all of these approximating parallelograms. Note that this parallelogram is not exactly on the surface, it's an approximation to that surface. So you can see a little bit sticking out off the surface here. As we do this, it's actually on the inside sticking out a little bit when we move there, right? But as we let delta u and delta v go to 0, these approximating patches are going to do a better and better job of giving our exact surface area for the region that we're talking about. Okay, I hope that that all is making some sense here. Let's go ahead and move on to our first example, example 18.1. Alright, so let's just remind ourselves that the formula that we're looking at is that the area of the surface over our given domain is the double integral over the given domain of the magnitude of the cross product of r sub u crossed with r sub v d capital A. So let's look at what is r sub u. This is going to be 1, comma, negative 3, comma 1, and r sub v is going to equal 1, comma 0, comma negative 1. So let's take the cross product here. We have r sub u crossed with r sub v. We might as well throw in our magnitude symbols and do that in order here in just a few moments. So we want the magnitude of 1, negative 3, 1 crossed with 1, 0, negative 1, which equals the magnitude of, so when I ignore my first row, I go 3 minus 0, then I ignore my second row, negative 1 minus 1 is negative 2, but then make it positive, then ignore my third row and get 0 minus negative 3 is positive 3, and so our magnitude here is the square root of 9 plus 4 plus 9, 18, 22, square root of 22. Alright, so our integral becomes, we want a double integral in the u direction, we're doing 0 to 2. So 0 to 2 in the u direction, negative 1 to 1 in the v direction. Our magnitude of our cross product is nicely just a constant here. And then we do this with respect to u and then with respect to v second. Alright, so here I then take the antiderivative with respect to u, and I get the square root of 22 times u evaluated from 0 to 2 dv. This equals the integral from negative 1 to 1 of 2 square root of 22 dv. This equals, I'm going to move up here, so this equals 2 square root of 22 times v evaluated from negative 1 to 1. So this is 2 square root of 22 minus negative 2 square root of 22 equals 4 square root of 22. So that should be our surface area for the part of this plane, this is a plane here, over this specific domain. Alright, so let's go ahead and give you guys a chance to do one. This exercise 18.1.1. Find the surface area of the helicoid, spiral ramp that is, with vector equation r of u comma v equals the vector u times cosine of v comma u times sine of v comma v over the domain d equals 0 to 1 crossed with 0 to pi in the v direction. Alright, go ahead and pause the video. Work through this as best you can. I will work through the solution myself and then go through that solution with you here in just a few moments. And we're back. Alright, so this is an example of a problem where we could really get caught up in the integration in a lot of different spots. I really want to see more than anything else that we're getting this set up correctly. And then we can talk through some of these integration processes as a nice review. And honestly, because I don't get a chance to do some of these hard integrals very often, and so it's nice to kind of practice them and go back through them because I actually think it's kind of fun. So the first thing we want to do is apply our formula. So we need r sub u, the partial derivative with respect to u, and the partial derivative with respect to v. I've done that in the top right box over here. So r sub u equals the vector cosine of v, sine of v, comma 0. And then r sub v equals the vector negative u sine of v, comma u cosine of v, comma 1. And then when we take the cross product of those two, we get r sub u crossed with r sub v equals the vector sine of v, comma negative cosine of v, comma u cosine squared of v plus u sine squared of v, which equals sine of v, comma negative cosine of v, comma u. When I take the magnitude thereof, I get the magnitude of r sub u crossed with r sub v equals the square root of sine squared of v plus cosine squared of v plus u squared, which equals the square root of 1 plus u squared. So this is what we want to take the integral of. So our area of this surface over the given domain equals the integral from 0 to pi in the v direction, 0 to 1 in the u direction, of the square root of 1 plus u squared du dv. So we could just plug this into the calculator at this point and get that the answer is approximately 3.6059, and you'll see that in the homework some of the questions literally just say set this up and find your answer that way. We actually do have a method of doing this by hand, so I am going to run through it and follow along as best you can here. Use this as a good practice for some of the harder integration techniques that you've come across in the past. So here we're going to do a trig substitution. We're going to let u equals the tangent of theta, so that du equals secant squared of theta d theta. When I do this, we have to change my u bounds from 0 to 1 to 0 to pi over 4. That's because if u is 0, then and u equals the tangent of theta, then theta must still be 0. And if u equals 1, then the tangent of pi over 4 equals 1, so the theta that goes along with u equaling 1 is pi over 4. So I change those bounds there. I change my integral to the square root of 1 plus tangent squared of theta, close my square root, times secant squared of theta d theta dv. Now we do the substitution because 1 plus tangent squared of theta is secant squared of theta. When I take the square root of that, I get secant of theta times secant squared of theta is secant cubed of theta. So this all equals the integral from 0 to pi of the integral from 0 to pi over 4 of secant cubed of theta d theta dv. Now this is actually a harder integral to take than we really would hope for at this point. This is going to take a by parts and then kind of a algebraic manipulation to work through it here. We're going to let w equal the secant of theta and dv equal secant squared of theta d theta. Then dw equals secant of theta tangent of theta d theta, and v equal the tangent of theta. Plugging in my parts, we get that the integral 0 to pi of the integral from 0 to pi over 4 of secant cubed of theta d theta dv equals the integral from 0 to pi of, big parentheses now, secant of theta tangent of theta evaluated from 0 to pi over 4 minus the integral from 0 to pi over 4 of secant of theta tangent squared of theta d theta, close that big parentheses, dv. So we have to do all this evaluation inside before we can do the integral with respect to v, but we're going to see some distribution done and then some moving bits around here. So the first thing we want to do is do this evaluation from 0 to pi over 4. When we do that, it actually works out to the square root of 2. I'm going to leave that to you, the listener, to go ahead and work through on your own. So maybe do that on scratch paper, just secant of theta, tangent of theta, evaluate it from 0 to pi over 4. You should come up with the square root of 2. So now we have that the integral from 0 to pi of the integral from 0 to pi over 4 of secant cubed of theta d theta dv equals the integral from 0 to pi, open big parentheses, of the square root of 2 minus the integral from 0 to pi over 4 of negative secant of theta plus secant cubed of theta d theta, close that big parentheses, dv. What I did here was that the tangent squared of theta equals secant squared of theta minus 1. So I went ahead and substituted that in and distributed this secant of theta across to get this result here. I then went ahead and distributed the negative and this outer integral across. So we have that the integral from 0 to pi of the integral from 0 to pi over 4 of secant cubed of theta d theta dv equals the integral from 0 to pi of the square root of 2 dv plus the integral from 0 to pi of the integral from 0 to pi over 4 of secant of theta d theta dv minus the integral from 0 to pi of the integral from 0 to pi over 4 of secant cubed of theta d theta dv. Now this is nice. This takes this algebraic technique now where we've duplicated our original question. This double integral of the secant cubed of theta shows up on both sides, so I can add it to the left, to both sides really, to cancel it from the right. So I have 2 times the integral from 0 to pi of the integral from 0 to pi over 4 of secant cubed of theta d theta dv equals square root of 2 pi plus the integral from 0 to pi of the natural log of the absolute value of secant of theta plus tangent of theta, all evaluated from 0 to pi over 4 dv. And so what I've done is the integral from 0 to pi of the square root of 2 dv, that is the square root of 2 times pi. And then here we could go through the proof of this integral for secant of theta, but at this point we've done enough of this hard integration where we're just looking up a integral table and knowing that the antiderivative of secant of theta is the natural log of the absolute value of secant of theta plus tangent of theta, and knowing that we need to evaluate that from 0 to pi over 4. Again, this double integral of secant cubed got moved to the left side, which is where that 2 came from. Okay, so this then implies that the double integral from 0 to pi and then 0 to pi over 4 of secant cubed of theta d theta dv equals the square root of 2 over 2 pi plus the natural log of the square root of 2 plus 1, all inside the natural log there, and then times pi divided by 2. And that's from evaluating the natural log of secant of theta plus tangent of theta from 0 to pi over 4, and then taking the antiderivative with respect to v, which is just a constant times v, and then evaluating that from 0 to pi. So again, you can work that out on your scratch paper if you'd like to, and then I divided both sides by 2 as well. So this then gives us our approximation of 3.6059. All right, I know there's a lot of details going on there. I would absolutely love it if you're following along with most of that, if not all of it. If you are getting stuck on some of these details and some of the trig substitution and all of that, I don't want that to be the biggest hinge here. Our new lesson for the day is using this formula of the cross product and the magnitude thereof and taking the double integral of that and getting all of that set up. That's really our key here. So in our next section here on the next page, we're going to start looking at even setting up these surfaces in parametric form to begin with, and then moving from there. And that's going to be something that I really want to see you be able to do. All right, so moving on. Let's go ahead and move to section 18.2, parameterizing a surface with a given domain to find the surface area. Example 18.2.1, find the surface area of the paraboloid x equals y squared plus z squared that lies inside the cylinder y squared plus z squared equals 9. Alright, so we need to have some strategy for parameterizing our surface. Our surface is x equals y squared plus z squared. When we say that it lies inside the cylinder y squared plus z squared equals 9, that's our constraint, so that's going to help us with our domain. So we'll get to that second. The first thing we want is to come up with our surface. Here I'm seeing a nice circular paraboloid with y squared and z squared, so it seems like a good first step to attempt y equals r cosine of theta and z equals r sine of theta. And if we do this, then we get x equals r squared cosine squared of theta plus r squared sine squared of theta, which just equals r squared. So this gives us the idea that S is a function of r and theta, and it equals r squared for my x component, r cosine of theta for my y component, and r sine of theta for my z component. And I believe this should work just fine. I do want to check on GeoGebra just to confirm, and it's always a good idea. I know in an exam we may not have that option, but as long as we're doing our homework, we should confirm that our thought processes are working out nicely. So here I've gone ahead and typed in that surface r squared for my x component, r cosine of v for my y component, r sine of v for my z component. And r we're going to have go from 0 to 3. My v, I'm going from 0 to 2 pi to go all the way around here. The r is from 0 to 3 is me actually getting ahead of myself. We'll talk about that on the worksheet here in just a moment. But sure enough, we do get that paraboloid. I guess I should type in x equals y to the second plus z to the second and just confirm, yes, they do perfectly overlap. So we have a good parameterization here. Going back here, then my constraints due to this cylinder is showing, well, y squared plus z squared, this equals r squared. Right, that is our x, it is our r squared, this equals 9, so this says that the cylinder has a radius of 3. So if we want to be inside that cylinder, we want to have my r value be between 0 and 3. And hopefully it's pretty apparent that we want to go all the way around this paraboloid inside of our cylinder. So we want 0 to be less than or equal to theta and less than or equal to 2 pi to go all the way around. So the area of this paraboloid for this, over this domain, is going to equal the integral from 0 to 2 pi in the theta direction and the integral from 0 to 3 in the r direction. And so we need to take S sub r, which equals, let's see, we get 2r comma cosine of theta comma sine of theta. And we get S sub theta, which equals 0 comma negative r sine of theta and r cosine of theta. We'll take the cross product here. And when we do that, we get, ignoring the first column, I get r cosine squared plus r sine squared of theta, I should be saying that. And then ignoring my second column, I get 2r squared cosine of theta minus 0. So that becomes negative 2r squared cosine of theta. And ignoring my last column, I get negative 2r squared sine of theta. Alright, the magnitude's going to take a little bit of work here. I'm going to move some things around so that I've got some room. Okay, so if I want to get the magnitude here and get it nice and simplified, I see that that's going to be a little bit complicated here. So first of all, actually, let's note that this is just r for that first one. So this is the square root of r squared plus the second component squared. So that's 4r to the fourth cosine squared of theta. No, this isn't going to be too bad. Plus 4r to the fourth sine squared of theta, which equals the square root of r squared plus 4r to the fourth. And if I factor out an r squared, we get r, and then take its square root, I get r, and then a 1 plus 4r squared inside. This actually isn't going to be too bad to integrate. We'll be able to use a substitution. So I have r times the square root of 1 plus 4r squared dr d theta. Okay, so this one we should be able to do by hand without too much effort here. let's see, I need room for a substitution. Let's move this to my left. So let's let u equal 1 plus 4r squared, so du equals 8r dr. So we'll have a 1/8 that gets thrown in here. I have the integral from 0 to 2 pi, 1/8 times the integral from 0 to 3, and then we have the rdr becomes the d theta, or the du, and the 1/8. So then I have the square root of u, du d theta, and I almost forgot to change my bounds, super important. So if u is, or I'm sorry, if r is 0, we get u is 1. If r is 3, we get 9 times 4 is 36, 37. So this is the integral from 0 to 2 pi times 1/8 of u to the 3/2 times 2/3, evaluated from 1 to 37, d theta. Now this is just going to give me a constant here, which I'm working out. Let's see, this is 1 over 4 times 3 is 1/12. I'll just write this in 2 steps, from 0 to 2 pi of 1/12 times 37 to the 3/2 minus 1 d theta. Now when I integrate with respect to theta, I just put a theta there and evaluate it from 0 to 2 pi. Is just going to add a 2 pi on here, so this is pi over 6 times 37 to the 3/2 minus 1. And I'm just going to leave that as an exact value here. So let's go on to exercise 18.2.1. For you to give a shot, find the surface area of the part of the sphere. So you need to look at parameterizing a sphere. X squared plus y squared plus z squared equals 9. That lies inside the cylinder. X squared plus y squared equals 4. Go ahead and pause the video. And I will work through the solution with you here in just a few moments. Alright, so we want to find the surface area of the part of the sphere x squared plus y squared plus z squared equals 9 that lies inside the cylinder x squared plus y squared equals 4. So let's recognize that this inside the cylinder bit is implying that this is our restraint. The surface that we're actually looking at is the sphere itself. So we parameterize the sphere, and I'm labeling that S, the vector S of theta comma phi equals the vector 3 sine of phi cosine of theta, comma 3 sine of phi sine of theta, comma 3 cosine of phi. That's our standard parameterization for a sphere. So then we take the derivative with respect to theta and phi respectively. So S sub phi equals the vector negative 3 sine of phi sine of theta, comma 3 sine of phi cosine of theta, comma 0. The partial derivative of S with respect to phi equals the vector 3 cosine of phi cosine of theta, comma 3 cosine of phi sine of theta, comma negative 3 sine of phi. We then go ahead and take the cross product of these two vectors, so the cross product of the partial derivative of S with respect to theta and S with respect to phi equals the vector negative 9 sine squared of phi cosine of theta, comma negative 9 sine squared of phi sine of theta, comma negative 9 sine of phi cosine of phi. And this last one, I did use a Pythagorean identity in order to simplify it down to this. We then want the magnitude of this cross product. The magnitude of S sub phi crossed with S sub theta equals 9 square root of sine to the 4th of phi plus sine squared of phi times cosine squared of phi. Again, there was a Pythagorean identity used for this, and then we simplify that. We can actually factor out a sine squared, and then we'll get a sine squared of phi plus cosine squared of phi that simplifies down to just 1, and then the square root of sine squared of phi is just sine. So this all equals 9 sine of phi. That's nice. That's not a horrible integral to have to take here. So to set up our integral, we need to understand what the restraint is in order to be able to set up our bounds. We know that this restraint is essentially saying that our radius equals 2 in the xy direction, right? Now, for the parameterization of a sphere, we actually have r equals 3 sine of phi. If we remember, here I have, say, my x radius, here's my z. So phi is measured off of the z-axis. So if we're looking at this point here, this is r, this is z. So, and this is rho. This is the distance from the origin to the point in question. So sine of phi times rho equals the radius here. And that's also how we got 3 cosine of phi is the z value in this direction. So recognizing that we have the restraint that r equals 2, we set r equals to 2, so 2 equals 3 sine of phi. So phi equals sine inverse of 2/3. So that's going to be my restraint on phi, is we want to have phi go from 0, so we're at the z-axis, out to the sine inverse of 2/3. We're going to leave it exact like that. We do not want to use our calculator here. It's just going to cause rounding errors. So the area of our surface equals, I pulled the 9 out, so 9 times the integral of 0 to 2 pi in the theta direction, and then the integral from 0 to sine inverse of 2/3 in the phi direction of sine of phi d phi d theta. Since our theta is separate from our phi here, we can actually pull this as 2 separate integrals, so this equals 9 times the integral of 0 to 2 pi of d theta times, I went ahead and did the antiderivative of sine of phi here to get negative cosine of phi, and we're evaluating that from 0 to sine inverse of 2/3. So this equals 18 pi times parentheses 1 minus the cosine of sine inverse of 2/3, close parentheses, close parentheses, close parentheses. This equals 18 pi times parentheses 1 minus the square root of 5/3, and the way that I'm getting that is recognizing that the sine inverse of 2/3 is looking at the triangle with opposite side 2, hypotenuse 3, and angle here, so that across from the 2, so that 2 is the opposite to the angle. Then our adjacent side to the angle has to be the square root of 5 by Pythagoras, and so then the cosine of this angle must be the square root of 5/3. So we're doing kind of a inverse and then taking the cosine of the angle without actually knowing what the angle here is at all. That way we don't have to do any approximations along the way. Alright, so that's exercise 18.2.1. Let's move on to section 18.3, determining the surface area for a function in 2 variables over a given domain. Alright, so suppose we have a surface given by z equals f of x comma y, and we want to find the surface area over a domain D. We can parameterize the surface as the vector r of x comma y equals the vector x comma y comma f of x comma y. So we're able to kind of re-look at this. So this is our basic situation, right? Z equals f of x comma y. We have a function in 2 variables, so we have a surface given that function, and we want to find the surface area given some domain. Then we look at parameterizing it in order to find our formula, and then we'll just use the formula moving forward here. So we set up our vector r of x comma y equals x comma y comma f of x comma y. Then we take our partial derivative with respect to x, so r sub x of x comma y equals 1 comma 0 comma f sub x, and the vector r sub y of x comma y equals 0 comma 1 comma f sub y. Then we go ahead and take the magnitude of the cross product, so the magnitude of r sub x crossed with r sub y equals the magnitude of 1 comma 0 comma f sub x crossed with 0 comma 1 comma f sub y, which equals the magnitude of the vector negative f sub x comma negative f sub y comma 1. So that's what we get when we take the cross product there. Taking the magnitude of this, we get equals the square root of 1 plus f sub x squared plus f sub y squared. And so this is the integral that we're looking at, is we want to take the double integral of this over our given domain. So thus the surface area can be computed via the double integral over the domain D of the square root of 1 plus f sub x squared plus f sub y squared d capital A. So let's go ahead and apply this formula in the next example here, example 18.3.1. Find the area of the part of the surface z equals 1 plus 3x plus 2y squared that lies above the triangle with vertices 0, 0, 0, 1, and 2, 1. So let's go ahead and draw out our domain so that we can see what the bounds for our integral are going to be. Looks like everything is positive, so we just need the first quadrant here. We've got the origin 0, 0. We have the point 0, 1. And then we have the point 2, 1. And so we have this boundary line between 0, 0 and 2, 1. We have the boundary line from the origin to 0, 1, and then we have the horizontal line from 0, 1 to 2, 1. Now the line from 0, 0 to 2, 1, this has a slope of up 1 over 2 and a y-intercept of 0, so this is just y equals 1 half x. So if we do in the y direction first, my lower bound is going to be y equals 1 half x, and my upper bound is going to be y equals 1, and then in the x direction we'll go from 0 to 2. So we then need f sub x, where, let's go ahead and define here, f of x comma y equals 1 plus 3x plus 2y squared. So f sub x equals 3 plus 4y, and f sub y equals, oh no, I totally am not taking partial derivatives correctly. That's just a 3, because the y is a constant. My f sub y equals 4y. And so we want to look at the double integral. In the x direction, we're doing from 0 to 2. In the y direction, we're doing from 1 half x to 1. And we want the square root of 1 plus 9 plus 16y squared dy dx. Now, if we go back and remember how painful it was to do this integral, where was it? Back here. Remember, this was a giant pain, and let's not go through all of this suffering again right now. Let's go ahead and just get out our calculators and do an approximation, or see if our calculators will do an exact value here. So I went into Wolfram Alpha. You could probably do this on TI-89 as well. We do get an exact value of 1/12 times 13 square root of 26 minus 5 square root of 10, which is approximately 4.20632. Alright, so the most important thing is getting this set up. Obviously, we need a lot of integration rules if we don't have the software that we have today. But for this, let's know that we can get it set up correctly, set up our bounds and all of that, and then if the integral is getting too messy, to go ahead and rely on technology to finish up the problem for us. All right, let's look on to exercise 18.3.1, last one of this lesson today. Go ahead and do this one as a now you try. (18.3.1) determine the area of the part of the cone z equals the square root of x squared plus y squared that lies between the plane y equals x and the cylinder y equals x squared. Give this one your best shot. I will be back with you in a few moments to hash out the solution with you. Alright, so it looks like this one is not too bad in the integration aspect, at least. So if I look at our domain, we're doing between y equals x and y equals x squared. So that's going to lie in the first quadrant between the point 0, 0 and 1, 1, where these two lines intersect. So if I draw the parabola y equals x squared, I get this parabolic shape from 0, 0 to 1, 1. That's a concave up. And then the straight line from 0, 0 to 1, 1, and we've got the space in between. So my y lower bound is the x squared, my y upper bound is x, my x lower bound then is 0, and my x upper bound is 1. So f of x comma y equals the square root of x squared plus y squared. F sub x equals x over the square root of x squared plus y squared, and f sub y equals y over the square root of x squared plus y squared. So the area is going to be given by the integral from 0 to 1 in the x direction of the integral from x squared to x in the y direction of the square root of 1 plus x squared over x squared plus y squared over x squared plus y squared dy dx. So the inside of this simplifies down to just a 2, so this equals the integral from 0 to 1 of the integral from x squared to x of the square root of 2 dy dx. So this equals the integral from 0 to 1 of the square root of 2 of x minus the square root of 2x squared dx. Moving on over to this next column, this equals the square root of 2 over 2x squared minus the square root of 2 over 3x cubed, evaluated from 0 to 1. And plugging those in, we get that this equals the square root of 2 over 2 minus the square root of 2 over 3. So that is the surface area of the part of the cone. Z equals the square root of x squared plus y squared that lies between the plane y equals x and the cylinder y equals x squared. And that's it. That's all I have for you today. Thanks everyone for listening. Have a great day, and I will talk to you in the next lesson.